Hello everyone. In this lecture, we are gonna go through dimensional homogeneity, which is very important for any physical equation that we write. And then after that, we are gonna solve one example of that, and we will introduce system of units. And after that, if we have time, we will go through ideal gas law, example, viscosity, definition of viscosity, and other introductory remarks about different types of fluids like Newtonian or non-Newtonian fluids. Okay, so let's get started with this dimensional homogeneity. This is very important for any equation, any physical equation in the world. Doesn't matter what equation that you solve, we have to make sure about the homogeneity of the dimensions on the right hand side, left hand side, and different terms of any equation. Okay, so for any equation in the world, the dimension of the left hand side of the equation, and here I want to introduce a kind of abbreviation for left hand side. Later in the course, if I use LHS, it means left hand side, and if I use RHS, it means right hand side. So the dimension of the left hand side of the equation must be the same as those on the right. So this is a very important principle for any physical equation in the world. Doesn't matter what field it is, any physical equation. When you write any equation that has units or dimensions, the dimension of the left-hand side and right-hand side should match, okay? Also, you cannot, for example, this is very important for dimensional homogeneity. You cannot add two parameters together or subtract them or divide them or subtract them. Not divide you might be able to do that, but just adding or subtracting two variables that have different dimensions. You cannot do that. For example, you cannot add velocity and area. These are two different variables, right? Have two different dimensions. For example, you cannot add 3 meters per second with 2 meters square, right? They have different dimensions. One has a dimension of LT minus 1, L length over time, and one has the dimension of length square. Does this make sense? No, this does not make sense, right? What does it mean? Like when you add 2 meter square to 3 meter or meter second, right? It doesn't matter. It doesn't make any sense. So this is a very important thing to remember when you are dealing with any equation, okay? So in general, you cannot add two quantities with different dimensions. So you can't add two quantities with different dimensions. Okay, so this is a general statement that you need to know. And now I want to have an example of this to investigate this dimensional homogeneity in an equation. Okay, so let's write an example. So investigate the dimension the dimensional homogeneity for the equation for the velocity or v of a uniformly accelerated body. Okay. So the equation for the velocity of a uniformly accelerated body can be written as this. V equals to V naught plus A acceleration times time. So V naught or V0 is initial velocity. A is acceleration, and T is time. Okay? So in terms of dimension, in order to investigate the dimensional homogeneity of that, we should write it in terms of dimensions. So this equation becomes, so velocity, as you may remember, the dimension of velocity was LT minus 1, correct? So I'm just going to write that one. It's going to be LT minus 1. And this is the left-hand side of the equation, okay? So, or LHS of the equation. And it should match the dimension of the right-hand side, okay? So let's see if it does or not. So the second term is velocity again. So as you see here, it is still a velocity, say initial velocity. So the dimension of that is going to be also LT minus 1. And then we have plus two terms. The first one is acceleration. So let's see what is the dimension of the acceleration. So the acceleration is going to be velocity over time, right? So we are going to have LT minus 2 times time, correct? Times time, which is going to be what? Is going to be t. So if you see, this one is going to be also LT minus 1. So we conclude all terms have the dimension LT minus 1, and thus this equation is consistent and homogeneous. Okay? So this was a simple example just to let you know, and so you understand how the dimensional homogeneity is applied in equations. And in any equation that you write, the left-hand side and right-hand side of the equation and all the terms in that equation have to have the same dimension. And here we also are adding two similar, two homogeneous or two variables that have the same dimension. So AT is also a velocity, although you are multiplying acceleration by time, but the dimension of AT is going to be the same as the dimension of velocity, okay? So they have to be dimensionally homogeneous and consistent. Okay, so now I want to solve another example. So this time I want to investigate the dimensional homogeneity for kind of a simple fluid problem that we will go through it in more depth later. But for now, just let's see how it is. So we have a tank of water which has an orifice. So this is the orifice of that. Okay. So the water is up to this level. And it is h, the depth of that. A is the area of the orifice. And then the water is just flowing out of this tank of water, okay? With Q as the discharge and discharge rate, and this is just a tank of water, and this is the orifice. Okay. So the volume rate of the flow Q is the volume rate of flow. And the formula of that here, we can use this formula for this particular problem as 0.61. The volume rate of flow is going to be 0.61 times A, which is what? Is the area of the orifice, times square root of 2gh. And g is acceleration of gravity. Okay. So the question is now investigate the dimensional homogeneity of this formula. Okay. So what we want to see what is the dimensions of different terms of this formula. So the answer is Q is the volume rate of flow. So let's just write the definition. What does that mean? Volume rate means volume per time. Okay. So it's the dimension of that is going to be volume is L cubed, right? Length times length over time. Time is going to be T. So this is going to be L3 T minus 1. Then we have area. So area is going to be A, or it's going to be length square, correct? And H, or we have height, which is H, is going to be what? The dimension of that is going to be length, correct? And we also have G. So G is acceleration of gravity. So it's acceleration. Its dimension should be like acceleration. So it's going to be length over time square, which is going to be LT minus 2. Okay. So now let's investigate the dimensional homogeneity of this equation. So the left-hand side is Q, or volume rate of flow. So it's going to be LT L cube T minus 1. Correct? I just wrote it from here. And then the right-hand side, we have 61, which is a number, 0.61, times area, which is L square, times square root of 2, which is also another number, times G square root of G, which is going to be LT minus 2 to power 1/2. And then we also have H, which is height, so it's going to be L to power 1/2, square root of that one too. Okay, so we have L3 T minus 1 equals to, from the left hand side, 61 times square root of 2. And then I just factor out all the terms. So I'm going to get, these two are going to give me this one and this one. Let me show it with another color. This one and this one are going to give me L, because it's L 1/2 times L 1/2. So it's going to give me L. And then times this L square is going to be L to the power 3. And then we have T to minus 2 to 1/2. So it's going to be T to minus 1/2. Okay. So as you see, from these two terms, they have the same dimension, right? L3 T minus 1. So this equation is homogeneous. So the dimensional homogeneity is valid here in this equation. And the other conclusion that we get is also the number (61) times square root of 2 is dimensionless. What do I mean by this? If the number had a dimension, any dimension, then the dimensional homogeneity of this equation would become invalid, right? So for example, assume, I'm just saying a imaginary scenario. So assume this one had a dimension of length, okay? So then the right-hand side of this equation would become L for t minus 1, and it was not the same dimension at the as the left-hand side, which is L3 t to the minus 1, okay? So this scenario could not be correct. So the only way these two, the left-hand side and the right-hand side, would have the same dimension is if this number is dimensionless. So this number, we can conclude based on this dimensional homogeneity, is gonna be dimensionless number, and doesn't matter in any system, in any units you use, it's gonna be the same number, okay? And we will come back to this, but by that what I mean by this. Okay. So to better understand this, I want to solve another example so you understand that the numbers can also have dimension in any equation, okay? So it doesn't mean that because this is a number in an equation, it doesn't have any dimension. So it's very important to take into consideration these numbers, and also in most of the equations, at least in fluid mechanics, we try to have dimensionless numbers. So if the units, the system of units is changed, we still have the same number. For example, something like here, which we have a dimensionless number. But now I want to give you an example in which we don't have the numbers also have a dimension. And you can find it by doing the same procedure of dimensional homogeneity that we had before. So investigate, in the new example, investigate the dimensional homogeneity of the equation the dimensional homogeneity of the equation of motion for a free falling object as the following. So h is the height of an object, a free falling object, and the equation that we have for that is 4.9 times t squared. Okay, so now I want to investigate the dimensional homogeneity of this equation. Okay, so answer. So on the left hand side we have height, which is the dimension of that is going to be length, okay? And on the right hand side we have 4.9, which is a number, times t squared. Okay, so when you write this, you see that the dimension of the left hand side is length, and here you have t squared. So how can this be correct? If we know that this equation is dimensionally homogeneous and correct. Okay? If we know that the only way it is possible for this equation to be dimensionally homogeneous is that the number 4.9 should have a dimension. Okay? So hence, in order to satisfy the dimensional homogeneity, the number 4.9 should be dimensional, or should have dimension. Should have dimensions. So now with this assumption, with this new assumption, let's rewrite the equation. So L is gonna be, and how the left-hand side can have the same dimension of the right-hand side. This is only possible if here the dimension of this number should be L times t to the minus 2, correct? Why? Because if that's correct, then these two are going to cancel out, and the right-hand side, the dimension is going to be L, the same as the left-hand side, correct? So this is the only way the dimensional homogeneity of this equation can be correct. So this is going to be the dimension of 4.9. Okay. So now I want to think a little bit about this. This is a free-falling object, and you have, most likely you have to study, you should have studied this during your physics course, right? It's a free-falling object. This is the dimension of 4.9. What is this? LT minus 2. It is length over time square. Length over time is velocity, but length over time square is going to be what? Is going to be acceleration, correct? Dimension of acceleration. So just think a little about this. What does this 4.9 represent? Just for a maybe, let's say I would give you 20 seconds to think about it. Try to remember, what does it mean? So if you recall, your physics course, so hence we understand and we conclude that 4.9 has the dimension of acceleration. So if we recall your physics course, in fact, it is what? What acceleration we have here in a free-falling object? It's gravitational acceleration, right? And in fact, 4.9 equals to 1/2 of g, or gravitational acceleration. And this is something you should have studied during your physics course, because it's a free-falling object, correct? So this is how we were able to find the dimension of this number by doing this dimensional homogeneity. And this is very, very useful and powerful technique in any physics problem, not just fluid mechanics, in solid mechanics, in all the physics problems. When you have an equation, you can just write the equation in terms of its dimensions, and all the terms in that equation should have the same dimension. Okay, even if you add this to another term, say 8, you can you can find the dimension of this 8, the number, by doing this dimensional homogeneity, and in fact it should be length, right? Because the dimension of the left hand side is length. So we should have the same dimension because we can only add length with length. And this is something you can get from these dimensional homogeneity arguments. And this is a very powerful argument, even when you try to do some experiments or even develop some new theory for any physical parameter. You need to take into account this dimensional homogeneity. You need to, your equations that you want to develop for any, for example, for a new theory or for a new paradigm that you want to do in any physics, any physical problem, this dimensional homogeneity should hold. And also, when you want to write something in an equation, and for example, in your regular homework or exam or whatever, in any course, you should be very careful about this dimensional homogeneity. Okay. Okay, so now I want to give you a brief overview of the system of units, and then after that, in the next session, we will go through the ideal gas law after a break. So, system of units. So we have two systems of units which are mostly widely used, and you need to know both of them in this course. The first one is international system, or we call it SI. And in this system, length, the dimension of length is meter. The dimension of time is what? Is second. The dimension of mass, the standard dimension of mass, is kilogram. And the dimension of temperature is Kelvin. Okay? We mostly use this system in our course, but I just want to note that you need to know, we also use British gravitational system that I'm going to introduce, but and that is very important for your engineering applications, for your engineering exams. If you want to take those exams, it's most in the U.S. and it's mostly in the U.S. that they use, and we use British gravitational system. But in the other countries, the mostly used system is international system. And also in the literature, in the scientific literature, if you write any paper, we mostly use international system and not the British gravitational system, okay, that I'm going to introduce now. So just one note that the fourth unit, also called Newton, in this system, or N, is defined as 1 Newton is 1 kilogram times 1 meter over second square. Okay. Although we don't need this, we can just write kilogram meter per second square based on the primary quantities, because these are the primary quantities, right? These lengths, time, and temperature are all primary quantities, correct? So we don't really need any additional dimension or any additional unit, and we can just use those. But Newton is, because the force is commonly used, we might also use Newton, because instead of saying like kilogram meter per second square, we can just say and we can just show it with N. And Kelvin is 1 centigrade plus 200 1 Celsius centigrade plus 273.15, just so you know. So these are for the international system. Okay. And then the other system is British gravitational or BG system. And in this system, we show length. The unit of length is foot. The unit of time is what? Is the same, is second. The unit of force in this system is pound. Okay? And the unit of temperature is what? This is something you have almost every day. You can hear it from all the weather news. It is Fahrenheit, right? It's mostly used in the US, but it's not the international system. And in the international system, it's Kelvin, okay? So you need the 1 pound, the force here in this British gravitational system is defined as what? 1 pound is defined as 1 slug, which is the mass unit, times 1 foot per second square. So the mass unit in British gravitational system is slug. In international SI system, it is kilogram, but here in BG, it is slug. And force is pound, and force in international system, it is Newton. Okay, so these are the differences, and you need to know these two systems well, and because in some of the exams, in some of the homework problems, we are going to work with SI, and in some others we are going to work with British gravitational system or BG, but mostly we are going to use SI in this course because this is the most accepted unit in the scientific community and the most kind of practice unit in the scientific community. And BG, you are going to need it for your work if you just want to become a civil engineer and then work in industry. This is mostly used in the industry and also in the US, actually. Just in the US, if you use that, this is very, very widely used. But again, in other countries, if you even in the industry, the SI unit is commonly used. So you need to know both of these systems well, and you need to know how to convert them to each other. So for example, 1 foot is around 0.3 meter, right? The second is the same, but kilogram the Newton and pound, you need to be able to convert them to each other. Okay, so you need to know all these conversion formula well, but in the exams you are able to bring one sheet of paper for yourself. So if you need all those formulas, you can just write those conversion formulas. So you don't need to necessarily memorize them, but you need to know their difference and how to convert them to each other. Okay.